Okay, so now let's move on to the third property, which is basically depression of freezing point. Right? Freezing point is basically when you're going from liquid to solid, right? And as you're going from liquid to solid, so you should understand that again the vapor pressure will decrease, right? And what is freezing point? Freezing point will basically be just a boiling point is when the vapor pressure is equal to the atmospheric pressure. Freezing point occurs at the point where the vapor pressure of the solid is equal to the vapor pressure of the liquid. So when these two vapor pressures are equal, that's when freezing occurs. When the vapor pressure of solid is equals to the vapor pressure of liquid, the freezing occurs. Right? Now, let's see the same way that we did the graph for elevation of boiling point. Let's see depression of freezing point. Okay. So this right here is your vapor pressure. This right here is your temperature. Okay. Now, if you had the pure solvent, this let's say was freezing at this temperature, which was TF naught. Can I call this TF naught, which was the pure solvent freezing at this temperature, right? Now, when you make it into a solution, you know that again, the vapor pressure decreases. So you know that the vapor pressure must decrease, right? This vapor pressure will decrease when you are what? Making it a solution or when you're adding the solute. So let's see, can you see this dip in the vapor pressure? This dip is when your vapor pressure is decreasing because you've added the solute. So now if I have a solution, let's say I have this solution right here. Right? Now, if you see that as the vapor pressure has decreased because of the addition of the solute, ये आपका solution है. This temperature right here will basically be the temperature at which it's gonna freeze now. This TF will be the temperature of freezing for the solution, and the TF naught was the freezing of the solvent. And now if you see the delta TF, do you see that the temperature has decreased? So can I say the delta TF, there's a depression of freezing point. Now if I want to find delta TF, how am I going to do that? I know TF naught is a greater value, so it's going to be TF naught minus TF, right? And you know, again, since this is colligative property here, it will depend on the molar concentration. It will not depend, it will be basically equal to the molality. It will not depend on the nature of the solute, but the molality. So you know that delta TF is directly proportional to the molality of the solute. Right? So I can write this as delta TF is equals to KF now, not inside the KB was the boiling point constant. This KF now will be what? Freezing point depression constant. KF molality. Where this KF now corresponds to what? It corresponds to freezing point depression constant. Also known as cryoscopic constant, also known as molar depression constant. Okay, now you can again put molality, you can equate it with what? Number of moles upon that. So you can write M molality as moles, which is W2 upon M2, where W2 is the mass, M2 is the molar mass of the solute, upon W1 upon 1000, right? And this will be written as what? W2 times 1000 upon M2 times W1, right? So you can replace that for M, and that will be what? Delta TF is equals to KF W2 times 1000 upon M2 times W1, right? And you can make M2 the subject because you can find the molar mass through the colligative property. So that will be KF times W2 times 1000 upon delta TF times W1. So you can again find the molar mass or identify a compound based on their colligative property. So if you have the colligative property, you can identify compounds, right? Now, the Kf and the Kb that you're using here in the equations here, how do you calculate or how do you find the values of Kf and Kb? So basically, I'm just going to tell you the formula. You won't be asked to calculate it, but just so you know that what formula you use to calculate the values of Kf and Kb. So Kf was basically the depression and freezing point constant, and Kb was boiling point elevation constant. Okay? So to find Kf, the formula you use is Kf is equals to R, where R is the gas constant, times M1, which is basically the mass of the molar mass of the solvent, times Tf square, which is the temperature, freezing point temperature of the solvent, right, square, upon 1000, times enthalpy change of fusion of the solvent. So how do you find Kf? Kf is R, where R is the gas constant. M1 is the molar mass of the solvent. Tf square is basically the temperature at which the solvent freezes. So the freezing point of the solvent alone, without the solute, not the solution, right? And enthalpy change of fusion of the solvent. That's how you basically calculate Kf. How do you calculate? You can just remember these formulas, right? Kb is calculated by R, gas constant. Kb is the boiling point elevation constant, right? R is equals to M1, again same, it corresponds to the molar mass of the solvent, times the boiling point of the solvent square over 1000 times enthalpy of vaporization of the solvent, right? Where Tb square is going to be, Tb is basically, Tb is equals to what? The boiling point of the solvent, right? So these are your colligative properties, and using these we're going to do osmotic pressure, and then I'm going to tell you why we end up with all these formulas ending with what? M2. Why are you finding the molar mass of the solute? Because through the colligative properties you can basically what? Find the molar mass of the solute, and when you have the molar mass you can basically identify them also, right? Now let's start with osmotic pressure.